Once again, when the function is smooth, we could use the formula. So it goes like this. If the function is continuous, for example, you fix y and solve for all the solutions, let's say x1, x2, etc. And also find the derivative dy by dx. And then the density function of y, which is what we are interested in, is given by this formula. So you essentially remember xi, the solutions are going to be in terms of y. So xi will be symbolically, of course, you can write it like this. For example, if y is, what I mean by solutions is if y is x squared, y is given, then there are two solutions, right? Plus square root of y and minus square root of y. So the point is both the solutions are in terms of, all the solutions are in terms of the given y. So let's try that quickly on this problem. Let's say x is Cauchy and the function is y equal to 1 over x. So in this case, we'll go with this, fix y. So how many solutions are here? If I fix y for x. What is that solution? x1 is 1 over y. And dy by dx is minus 1 over x squared. And remember, we need the absolute value. So that will be absolute value of this. And then you plug in x1 equal to 1 over y. So this will come out to be y squared, right? So step number 2. So step 3 is there is only one solution. So fyy is 1 over y squared. Then in the density function of x, which is here, you plug in for x, x1. So this is going to be a over pi 1 over y squared plus a squared. So let me rewrite it here. So this is going to be fyy would be, so notice y squared goes inside. So this becomes a squared y squared. So you can also write this as right? Isn't it? I just pull out a squared outside. So this becomes 1 over a, right? So multiply by which? You pull out a squared from here, a squared from here, so that a squared cancels, right? So what is this form? Anybody? What is that form? Is this form familiar to you? Yes? To anybody? What is it? What is that density function look like? If we want to, is it Gaussian or something else? No, that's also Cauchy because that form exactly looks like, look at that. What is the Cauchy form? 1 over a quadratic, x squared plus a squared. That's y squared plus, so only difference is that's the reason I purposely wrote it that way. If I replace that here a by 1 over a, you get that form, right? So moral of this, here is a theorem. If x is Cauchy, then 1 over y is, 1 over x is also Cauchy with the parameter flipped. So this is what, so you have a theorem now. Y is, so if x is, if x happens to be Cauchy with parameter a, then 1 over x is also Cauchy with parameter 1 over a. Now you ask me why, that's why the proof is here, okay? So this is where, so we have been able to make a conclusion, a theoretical conclusion. And results like this. And remember, if you had, hopefully you have looked at the videos and so on. We have a couple of other results on Cauchy and relating uniform, etc. Right? So for example, if x is Cauchy with the parameter, you put a equal to 1, right? That's what then if you define theta to be tan inverse of x, then theta is what? Anybody? So anyway, you should go through if you haven't gone through it, that's again a very standard result, uniform. But if it is any other a, it's not uniform, etc. Let me just, pretty soon I will be done with at least one random variable unless you have, so moments in general, it's expected value of gx, right? So that's gx multiplied by the density function of x dx. Or it could be, if it is a discrete, we will use this formula. What is it? So a characteristic function is a special case of moments. So that's E. A characteristic function is e to the power j omega x. So remember, gx is a special gx. Now, so I'll quickly, we went through all this last time, right? So the simplest mean is, of course, the simplest moment is the mean, which is expected value of x, which gives you an average value. All of us know this, right? X. But given a density function, you should be able to compute this. So if this is, how about the limits? It all depends. If it is Gaussian, it goes from minus infinity to plus infinity. If it is exponential, this is from 0 to infinity. So I gave you a few homeworks. Now, you have to run with the class. If you don't practice it out and you look at the solution, it's not going to be helpful, right? And similarly, the variance is deviation of the actual random variable from its mean. And since the deviation could be plus or minus, so it's like a mean squared error. So again, very physical quantity. And it is what it is. You can compute it, right? It also has this way. So you can also compute it. If you don't want to do this separately, if you know the first moment and second moment, you can compute the variance. And I gave you the interpretation, right? If a density function is like this, and you say this is the mean, and you mark saying that this is the mean plus sigma, mean minus sigma, or mean plus k sigma and mean minus k sigma. So you're asking the question, what is the probability that the random variable lies here? Then last week we actually have a hold on this through Chebyshev's inequality, remember. It said the probability that the random variable will lie in this region or will lie outside this region is, the probability is less than sigma squared over epsilon squared. Epsilon is k sigma, so this is 1 over k squared, right? Interesting thing is this is irrespective of the actual distribution. So these are, if a random variable is like this, you can sort of guess mean is here. So if another random variable is like this, that also has the same mean. But clearly you can see most of the action here is going to be in this neighborhood, whereas here things could be all over. That's where the variance helps. You will see naturally the variance here will be small, whereas this has a larger variance or dispersion, right? Dispersion around the mean. So that the physical quantity, you can go to the kurtosis and so on, the third order moments and the fourth order moments. So in general, it's a good idea to, what if you have two distributions where both these means are equal? Then you have to go into it. Somewhere it's going to be different, right? So you may have to go to a higher order characterization, etc. And so let me also show you an application of the characteristic function. Maybe you can close that first one, just stop it here.